So good afternoon to all. In previous classes we finished the different topics like self-regulation, servo operation, self-regulating systems, what are the different process dynamics elements, different process variables we've seen. So now in today's session, how the elements or affect the different processes, like which systems or acts like a different those how we are relating to the electrical systems. In today's session we will see. So basically two systems are there, that is two elements are there, which is a resistive element and capacitive element. How we are going to relate the electrical systems into our normal mechanical systems, like how we are going to use in the processes. So first, which is a resistive element, we already know that that is a which is having a resistive that I am showing in the slide, which is having two terminal device. This is a two terminal device which having a potential of E1 and E2 with the two ends. The current passes to that resistor is, let us take that is I. If by the Ohm's law, what is the resistance value here? R is equals to I in V by I. So or nothing but V is equals to I into R we can write. So this we can relate into the normal process industry where the flow exists. Like in normal pipes we are going, there exist some restrictions with the walls. So there the resistance will exist. So here in the next diagram I'm showing that one, which is having a continuous pipe. So which is having the flow of H1 and H2. We are going to control the flow rate of the pipe by using a restriction, that is that restriction is called as a valve. So here we are going to control the flow rate, nothing but the flow rate is controlled in that particular pipe. Here current passes through is controlled in that resistor, here the flow rate is controlled in that particular pipe. So these two are interrelated, the electrical system as well as a mechanical system. So resistance we can replace it with a pipe which is having a restriction. So here we are showing that potential difference, that is E1 and E2, there the flow rate is different. So flow rate is differ before the restriction and after the restriction. So that is H1 and H2. So we can write the formula like, here I is equals to, we are writing E1 minus E2 by R. There we can write that formula, that flow rate, here is a current, there is a flow rate. So we can write Q is equals to H1 minus H2 by R. Okay, so H1 minus H2 by R we can write. Here E1 minus E2 by R we are writing as a current, there flow rate of that particular pipe or restriction we are going to take Q is equals to H1 minus H2 by R we can write. So capacitance, next element, the next basic element we are going to use in a process industry, that is a capacitive element. How we are relating into the normal industries. So capacitance, which stores the energy in the electrical form, that is a electrical capacitance. Here the capacitance that can be worked out wherever the storage capacity, wherever the storage is there, storage compatibility is there, that will possess a capacitance element. So here you can see in this one, which is capacitance here and which is a storage tank there. So capacitance, which is also a passive two terminal device, that will maintain a potential of E1 and E2, that will stores the potential of E1 and E2. Current passes to that one, let us take that is I. So we can write the current value, that I in the capacitance C into dV by dt, where we are taking E1 minus E2. The difference of potential, the derivation of difference of potential we can take. So I is equals to C dV by dt we can write. So here storage tank. So storage tank, that will store the value. So that will stores the water or liquid, whatever the fluids we are going to dump into that one, that will store without any disturbances. Here we are applying the flow, that inflow rate with the value of Q, that all water comes into the tank and that will stores that value with the height of or with the level of H there. So here H is a storage element and here flowing is a Q is a flow element. There in the capacitance, electrical potential, that E1 or E2, that is a storage element here, and here I is a flowing element. So here we written that one is a I is equals to C into dE by dt. So here we can write it as, here what is a flowing element here? Q is a flowing element. So Q equals to, here that will stores that capacitive constant is C we are going to represent. So C into what is the storage element here, that is a height of that particular tank or height of the liquid. So dH by dt. So we can write the equation in the capacitive element, that is Q is equals to C into dH by dt. So these are the two basic elements we are going to use in the process dynamics. One is a resistive element and capacitive element. Once again, the resistive element we can write is as a Q, which is in a particular, which is in a flow of a pipe, which is having a restriction there. So Q is equals to flow rate of that particular liquid, Q is equals to dH by dr. Okay, dH by dr. Next one, if capacitance is there, that value is equals to Q is equals to C into dH by dt. Okay, so we'll move on to the next slide, which is elements in the mechanical translational system. So elements in the mechanical translation system, basically three elements we are going to use in the mechanical translation system, which is a mass, dashpot as well as a spring. So where, for example, this is one element. So this is one element. When you apply force to this particular mass or particular element, this will move away from that force. It will move away from that particular force. And when you apply force, that will having a mechanical movement. So that will having a mechanical movement, nothing but that will displace from one place to the original place to the another place. So this displacement, whenever what you are applying here, you are applying the force. So force you are applying, so that acts like an input that will displace according to the force what you applied. So that will displace. Displacement is a output. Here the mechanical translation system is nothing but whenever you apply force, so that will displace from one place to the another place in a linear fashion. So that is called as a mechanical translational system. Basically mechanical translation systems are divided into three types. One is a mass, dashpot as well as a spring. Mass, dashpot, spring. So for three diagrams you see, we are applying force here, they will display according to the double derivation or single derivation or any no derivation. So here, which is the output of that particular one is a displacement. Okay, so output is displacement, input is a force. So based upon these mechanical translation systems also, the process dynamics will work out. So next I will see the different elements in the process dynamics. So basically the elements in the process, those are divided into basically four categories. First one is a proportional element, capacitive element, time constant element and oscillatory element. So you already came across with the different signals, whatever you learn in the signals and systems, which is a proportional element, that is unit step signal, ramp signal, exponential signal and impulse signal. So likewise here, each and every element in the process dynamics, they will produce individual responses. So according to the response produced, those are divided into four categories: proportional element, capacitive element, time constant element, oscillatory element. We already seen what is a resistive element and what is a capacitive element, how they are acting in a particular process dynamics and how the response will be, that we can see in this proportional element and capacitive element. First two are related to entire resistive and capacitive element. If we combine the resistive element and the capacitive element, those are which is a time constant element. And if we use any mechanical translation system in a particular dynamics, that is about the oscillatory element. So we will see the proportional element first. So this is the proportional element, I already told, which is a resistive element. Whatever the resistive element we are going to use in a process industry, that acts like a which is a proportional element. You see the above example, that is above diagram, which is having a pipe there, no? So that pipe which is having a inflow rate M. So that inflow rate M, according to the flow rate, here we are going to measure the flow rate by using a manometer. So where we kept a manometer which is having a H1 height, H2 height like that. So the difference of two heights that will measure the flow rate, that is we are indicating with a head of that C. C is a head, that is a flow rate of that particular pipe. So wherever we have a pipe connection, I already told wherever we have a pipe connection in a particular process industries, that will acts like a resistive element. So how it acts like a resistive element? Why? Because here we are placing a restriction, that is wall. When you operate that wall, if you close that wall, flow rate will be closed. If you open that wall, flow rate will be maximum. Like that, it will resist the flow rate of that particular pipe. So that is that element is called as a resistive element. So here resistive, we already written the equation for the resistive element. What is that one? Which is I, that is current flowing, that one I is equals to V by R, or else that flow rate we are going to take. So flow rate, that is nothing but Q is equals to whatever the height H by R we can write. So here what is a flow rate here, which we are taking? M is a flow rate, C is our height. So C is our height, that is nothing but potential, which is a V. So we can write flow rate is equals to M is equals to C by R, or else C is equals to M into R. So C is equals to M into R, where C is the output voltage or output whatever the height that will maintain. M is the input whatever you are applying, that is a flow rate. So that R is a resistive constant. So here we can indicate, or we can analyze the total entire diagram with a single block. So that inside block we are having a constant value, that is R. So that input we are applying, that is M here, and output we are getting, that value is C there. So we can write C is equals to M into R. So we are getting C is equals to M into R. Okay. So we will see in the next slide, this is that one. So proportional element, that can C is equals to M into R, where R is a constant and C is a output flow rate or output whatever head we are taking, M is a input flow rate. So which C is proportional to M, nothing but when M changes, that C value is also changes, and which is about a constant element. So that will maintain a unit step signal as a response. So next we will go for the capacitive element. So capacitive element, I already told, that is capacitive wherever the tank is there. If the tank is having a storage capability, that will act like a capacitive element. So that will act like a capacitive. So here I am taking a tank, so which is having an inflow. So according to the inflow of a pipe, the tank will store the water. So here inflow rate I am considering as a M. So according to the flow rate, that will maintain the height of H, that is C, let us take, that is the head of that particular tank. So here we are going to monitor the output of this particular response or particular tank here. So how it works? I already told that capacitance, whenever a tank is there with the inflow rate, we can write the flow rate of a pipe, flow rate of that particular tank, Q is equals to, that is C into dH by dt we can write. So here, what is the inflow rate we are taking? M is the inflow rate. So what is the height of this one? That C is we are going to take. So we can write that formula, M is equals to C into dC by dt we can write. M is equals to C into dC by dt. So whenever you apply Laplace transform here, so you apply Laplace transform C into d by dt of C, nothing but which is S into C equals to M, we can get. So what is C here? Small c, that will indicate the output. So you write the equation for the output, that C is equals to 1 by Cs into M. That output flow rate is equals to some constant, which is 1 by Cs into M here. Okay. So M is the input flow rate, C is the output that you are going to get. Whatever the constant, 1 by Cs multiplied with the input flow rate. So entire that system we are going to represent with a block. So block diagram, which is having a 1 by Cs as a constant that we are writing in the inside of that particular block. That block is consist of a input of M, that is we are going to indicate C as a output. So we can write like this, that response of capacitive element, which is, I already gave the derivation, that is C into dC by dt is equals to M. You apply Laplace transform there. So Cs into C is equals to M. So C is equals to 1 by Cs into M. So which is S. S is nothing but which is a time response that will vary according to the time. So that here we are going to get a ramp response in the capacitive elements. Okay. So this is about your proportional element, capacitive element, which are same as a basic elements in the process dynamics, that is a resistive element as well as a capacitive element. Okay. So next we will go for the third one, which is a time constant element. So in electronics you already learned what is meant by time constant. That is a product of resistance into capacitance, that is T is equals to R into C, we can write. So here also if we combine R into C, nothing but a combination or a cascaded version of the resistance and capacitance. Here also we are going to combine a resistance as well as a capacitive element. So resistive element, what is a resistive element? The flow rate of a pipe which is having a restriction. So if we add the pipe with a restriction with the storage tank. So a storage tank which is having a outflow with a restriction. This entire construction is called as a, which will maintain the element like time constant element. Okay. So you observe here up to this tank level, up to this tank, that will act like a capacitive element. Only that output flow rate with the restriction, that will act like a resistive element. Here we are going to cascade these two. So cascading means we are combining those two elements individually, that will maintain a time constant element. So which is having the inflow of M, outflow of R. Okay. So outflow of whatever the Q you are going to take, or C, whatever the value you are going to take here. We are combining those two. We are combining those two means we are going to get like which is a high pass filter which is having a capacitive element as well as a resistive element. So by that you, if we calculate the value which is R by RCS plus 1 you got. So R by RCS plus 1, RC is nothing but a time constant, that is T. So we can replace that one with a R by Ts plus 1 we can write. So that entire system we are going to replace with the block. That block which is having the input of M here and output of C. Okay. So input M we are, that flow rate we are going to apply, C that output we are going to get here. Okay. So next we are going for, this is a response of a time constant element which is a exponentially increasing. Unit step signal, that response is a resistive element, and ramp signal which is a capacitive element, time constant element which is having a exponential signal. Finally, which is last one, that is oscillatory element. So oscillatory element, oscillations, where it produces the oscillations. Whenever you have a second order system, so if a construction is having a second order system, that will produce as oscillations. We have different types of responses that will produce as, which is having overdamped system, underdamped system, critically damped or undamped system. Wherever that will produce is the oscillations there. So oscillatory system is also related to that one, where we are going to join all the elements, all the mechanical translational elements, then that will act like a oscillatory element. What are the mechanical translational elements we have? Three. The first one is a spring, dashpot as well as mass. So if we combine these three elements as shown in figure, so that will act like a second order system. That second order system is a oscillatory element. So you already know the equation in the control systems, that second order system equation, which is omega n square by s square plus 2 zeta omega ns plus omega n square. This is a second order system equation where omega n is a natural frequency and zeta is a damping ratio, like that. So here if we write that second order system equation in a single block with a having of input, here in a process industries, whatever the input is a flow rate, output you are going to get, here we are taking a liquid process. So that entire system is having an input of M, which is a flow rate, output that is a head of a particular tank. Okay. So you are applying input here and you are getting output there. So this is a second order system. So the response of the second order system is a oscillatory. Oscillatory nothing but which will produce is these type of waveforms, which is overdamped system and critically damped system and underdamped system. Okay, underdamped system which is having oscillations. So overdamped system that will reaches somewhat early when the critically damped responses. So this is about your oscillatory element. So in the next class we will go for the what is a interacting system and what is a non-interacting system. We'll see in the next class. Thank you.